Part A is pretty straightforward. We're trying to work out resistance. We know resistance is resistivity times length over area. Resistivity is 1.12 10 to the minus 6. The length is 1 meter. And we divide that by the area. So area is pi r squared. And radius, because we're given diameter in this case, radius is diameter over 2. So our area equation becomes pi times d over 2 squared. So putting that in our equation numerically, we get pi times 4 times 10 to the minus 4 over 2 squared. And if we type this in, we end up with 8.913 ohms, which rounds to 8.91 ohms to 3 significant figures. That's the number of significant figures all the numbers are given to us in this question. For part B, part 1, so we have a wire. It's the same wire as before, so it's a meter long wire. The question is asking us to explain how the potential along the wire varies with distance from A when the switch is closed. So if we were to connect a voltmeter, one terminal of this voltmeter at A, and then another terminal, this is a sliding terminal. If we were to move this terminal from A all the way along to B, then what we would pick up is the potential along the wire as distance varies from A, which is what the question is asking for. So the question is basically asking for, how will this voltage vary as we move the terminal from the left-hand side all the way to the right, as we increase distance from A? So imagine if we were to, where this terminal is, imagine splitting this wire into two parts. So we have one part here, one part here. Let's say this part of the wire has resistance R1, this part has resistance R2. Whatever the ratio of resistances would be, R1 to R2, that would be the ratio of voltages across those two parts of the wire, which is the case for resistors in series. So V1, V2, that would be the ratio of voltages. An equation for the total voltage across that portion of wire, so I'll call that V1, that would be equal to R1 divided by the total resistance. So the total resistance, let's just call that RT. Total resistance is just the resistance of the wire. We multiply that by the EMF, and that would be the voltage across this portion of the wire. So because the total resistance is constant and the EMF is also constant, we can see from that equation that the voltage across that portion of the wire is proportional to the resistance that it is in parallel with. And as we know that resistance is equal to resistivity times length over area, resistance is proportional to length, and if voltage is proportional to the resistance that it is in parallel with, therefore voltage is proportional to length. That's just combining these two things together. So let's phrase that to get some marks for this question. So for part 2, showing the potential difference between A and a point 75 centimeters along the wire is about 1.1 volt. We can use the same theory that we discussed in the previous part to answer this. So we know that whatever fraction of the wire that the voltmeter is in parallel with, and in this case, so the fraction of the wire that it is in parallel with would be 75 over 100, or 3/4. That will be the fraction of the total voltage that the voltmeter will read. So the voltage available is 1.5 volts. The voltmeter is in parallel with 3/4 of the total resistance, and therefore the voltmeter picks up 3/4 of the available voltage, which would be 1.125 volts. And finally for part C, so we have a circuit where we have the same wire as before, but in parallel with that wire we have two resistors. And we have an ammeter going from one parallel branch to the other. And we're told in the question that the ammeter reads 0 amps because the potential difference across the ammeter is 0. So if you were to place a voltmeter here, that voltmeter would read 0 volts. And then we're trying to work out what the resistance of R would be. So the reason that there would be 0 volts across these two, or how we can achieve that, how we can get 0 volts across those 2 points, is if the voltage across this part of the wire and this resistor are equal, and similarly if the voltage across this part of the wire and this resistor are also equal. If that's the case, so we can work this out numerically. So if this is 75 centimeters, this will therefore be 25 centimeters. And this is a ratio of 3 to 1. And actually we already worked out in the previous part that across this portion of the wire, because that represents 3/4 of the total resistance in this wire, it therefore gets 3/4 of the voltage. You will have 1.125 volts here and 0.375 volts there. And I got that 0.375 from doing 1.5 minus the 1.125 volts. So that gives 0.375. That's the case because these two branches are in parallel, so they each receive in total 1.5 volts. And then these two parts of the wire are in series, so their voltages will add up to make 1.5 volts. So if this is the case, then there must also be 0.375 volts here and 1.125 volts there. And there's a few ways in which we can then work out the resistance of R. So I'll just work out the resistance of R and then we'll go back to explaining a bit more about this scenario. So I think the easiest way is to use ratios. We know that the ratios of resistances should be 3 to 1, as we saw from the lengths that we have here, 75 to 25, that's a ratio of 3 to 1. The voltage is therefore split in the same ratio, 3 to 1. And that's the same thing here, again, 3 to 1. And therefore the resistances here should also split in a ratio of 3 to 1. So 3.3 to this unknown resistance R should be in the same ratio of 3 to 1. And we can see that R should therefore be equal to 1.1 ohms. So just to make sure that we get all the marks for this working, we could include a couple of extra bits. We could write down that 75, if I actually just rub this first bit out. So we can start with saying 75 to 25, that's the same ratio as 3 to 1, and 3.3 to R should be in the same ratio. And I can write this as a fraction, R over 3.3, so this divided by this, should therefore be equal to 1 over 3. R is then 3.3 times 1 over 3, which would be the 1.1 ohm that we're after, which is our answer. Okay, so then just going back to this scenario, to just explain a bit more about how the voltage here could be 0. Or why that is the case. Why is the potential difference across those two branches 0? Why do these voltages have to be equal? So let's think about charge traveling along this wire. So I'm going in the direction of conventional current for no particular reason. I'm just going this way. That conventional current splits in this branch and in this branch. And if we think about what voltage means, voltage is defined as the work done per unit charge. So when charge passes through, or when 1 coulomb of charge passes through that 1.5 volt cell, it gains 1.5 joules of energy. So 1.5 joules of energy per coulomb is gained as we move through this cell. And as we move through these two resistors, well, the resistor and the wire, we're going to lose 0.375 joules for every coulomb of charge that passes through those two components. Well, if we had 1.5 joules per coulomb to start with, and as a coulomb of charge goes through here, or per coulomb of charge, and as that goes through here as well, we lose 0.375 joules. Well, then at these 2 points, we have 1.125 joules per coulomb left over. And if the charge has the same energy there and there per coulomb, then the potential difference across those 2 points should be 0. It's only if the charge carriers have differing amounts of energy at those 2 points will there then be a potential difference.